A chunk of graphite looks solid, but zoom in, and that mass dissolves into a rigid geometric grid of individual carbon atoms. Chemical reactions occur between individual atoms in set ratios, but we interact with chemicals as bulk mass. A balanced equation may call for 2 atoms of hydrogen, but a laboratory scale only reads in grams. To bridge these scales, one carbon-12 atom is 12.0 atomic mass units. In the laboratory, we aim for exactly 12.0 grams. Scaling up requires a constant, 6.02 times 10 to the 23rd power, Avogadro's number. Gathering that exact quantity creates 1 mole of carbon. This makes the mole a central coordinate for calculations. It allows us to move from the number of particles we cannot see to the physical quantities we can measure. Every chemical calculation routes through this central point. The first connection we establish is between the mole and physical mass. We define this path using molar mass, the weight in grams of exactly 1 mole of a specific substance. For silver sulfate, we sum the masses of its components. We multiply 2 silver atoms at 107.9, 1 sulfur at 32.1, and 4 oxygens at 16. These add up to 311.9 grams for every mole of the compound. Dividing mass by this molar mass gives moles. Multiplying moles by molar mass returns total mass. While mass is what we measure on a scale, converting it to moles reveals the actual number of particles available to react. While solids have a fixed mass we can easily weigh, gases are characterized by the volume of the container they fill. Because a gas expands and contracts based on its environment, we must measure these volumes at standard temperature and pressure, or STP. Avogadro's hypothesis states that equal volumes of different gases, at that same temperature and pressure, contain the exact same number of particles. This provides a predictable constant. At STP, 1 mole of any gas occupies a volume of exactly 22.4 liters. We can now add a second pathway to our mole hub, specifically for gas volumes. To find the moles in a gas sample at STP, we divide the volume by 22.4. To find the volume from moles, we multiply. This allows us to determine the particle count of a gas sample simply by observing the space it takes up. These conversion paths allow us to work backward, using laboratory measurements to determine the internal structure of an unknown compound. Consider a substance that is 81.8% carbon and 18.2% hydrogen. If we assume a 100-gram sample, those percentages become 81.8 grams and 18.2 grams. We route these masses through the mole hub by dividing carbon by 12.0 and hydrogen by 1.0. This reveals a molar ratio of 3:8. This lowest whole number ratio defines the empirical formula, C3H8. The empirical formula represents the simplest ratio, but the actual physical molecule may contain whole number multiples of those atoms. We find the true molecular formula by calculating a whole number multiple, N. We divide the actual molar mass by the empirical mass. Multiplying the empirical formula by N identifies the exact number of atoms in the physical molecule. The mole acts as a bridge between bulk weight and the precise atomic blueprint of the substance. In the liquid state, chemicals are dissolved into a solution, rather than existing as pure solids or gases. We measure these concentrations using molarity, defined as the number of moles of a solute per liter of total solution. Diluting a solution involves adding more solvent. The liquid swirls and diffuses as the total volume of the mixture increases. While the total volume increases and the concentration decreases, the absolute number of solute particles in the container remains constant. If we take 200 milliliters of a 0.5 molar solution and add 300 milliliters of water, the volume rises. The particles spread out. Since moles don't change, initial molarity and volume equal the final molarity and volume. By rearranging these variables, we can find the exact concentration of any resulting mixture. Using moles as a constant allows for precise control over chemical intensity by simply adjusting the volume of the solvent. These different pathways connect to form a single framework for chemical analysis. Each route is defined by a specific factor: molar mass for weight, 22.4 liters for gas volume, and Avogadro's number for individual particles. This network allows for multi-step calculations. We can measure the mass of a solid, convert to moles, and then determine the volume of gas that substance will produce. This process relies on dimensional analysis. If the units cancel out along the path, the resulting calculation will align with the physical outcome. The mole provides the standard unit that links the atomic scale to the laboratory scale. It functions as an operating system for chemistry, making the behavior of the invisible atomic world predictable through macroscopic measurement.